Hello guys, welcome back to Bear20's Projects. In today's video, I'll be sharing my CPU design with you guys today and my CPU architecture. Now, I haven't posted in a couple months since I've been working on this. This has been like my sole project pretty much, and so this has engulfed much of my time. But before we look into the actual CPU, I want to show you guys the diagram or the architecture of this thing. It's quite simple, contains 4 blocks. We have the input block, we have the 3 blocks inside the CPU. So you have the RAM, the ALU, and the control unit. My goal was to make an architecture that was incredibly simple, just as a proof of concept. Can you understand it? Can you not understand it? And for it to compute complex things with such a simple architecture with very limited clock cycles. The goal was for it to be efficient and simple. Now, this part's the actual CPU, this thing contained inside the box. This thing out here is the input, what actually feeds the CPU what to tell it. So this is the clock and this is the instructions. The instructions do not come in via serial input. As I look here, they actually come in via parallel input. My current design on the breadboard is a 4-bit. So this is a 4-bit parallel input for each clock cycle, not a serial data input. So this looks kind of deceiving, I'm afraid, sorry. Now the 3 blocks inside the CPU are quite simple. Your RAM, your ALU, and your control unit. Inside the ALU, we have 3 registers. We have the A register, B register, and we have our C register. A and B are your 2 operands for the ALU. Your C register is your accumulator, or your output. And the RAM just interacts with those 3 registers. So it reads and writes to A, B, and C registers, and mostly writes to A and B, and mostly reads from the C register. And then so it can feed a number into the A register and B register, perform an operation on it, store that output, and feed it back into the input. Or it could either output that current number. Now we also have the control unit. The control unit handles the clock data, like the current instruction to be fed, and just activates and deactivates signals on the RAM and the ALU. Without this, these things would not know how to work together efficiently. This basically decodes the input from the data lines and feeds that into a usable output for the CPU or micro operations for the RAM and the ALU. This is the most basic design I could think of. That was the most efficient. Later, I first built on a breadboard. I'll show that up on screen now. And this breadboard it was very large. My first attempt failed miserably, but my second attempt worked pretty well. And I was able to do basic arithmetic operations and move data around. But for it to be more stable, I wanted to put it on a breadboard. So I made this. So this consists of 2 parts. The first part is we have our CPU itself. That is this part of the design. And then we have our control block. This is what feeds the instructions and the clock into the CPU. First look at the control block though. The control block consists of 8 ICs. This part up here is the clock generator. And so this is just binary counters, and this is also a binary counter. And so this feeds a usable 4-bit data input to the RAM. And now, if you notice here, we actually have 3 RAMs. We have this one, and this one. And that is for my 3 parameters for my instructions. So we have our opcode RAM, our ARAM, and our BRAM. Now all 3 of these feed into the CPU via these male header pins here. These header pins right here. And so the clock's output, or the clock goes into the counter's output feeds into the RAM address out, and the address feeds into the RAM, and the RAM now spits out a number that is programmed via these dip switches right here into this. Now, once that output from the RAM, it feeds into the CPU itself. The CPU consists of around 2 to 3 parts. The ALU itself, this is a 74LS181. This is the heart of it, so it can do comparison operations, arithmetic, and logical operations. And then you have our A and your B registers right here. And in this scenario, this is actually RAM, not registers. So this was slightly more complex, but these are just for the sake of education, this is registers here. So we have A or B and registers that feed into the RAM. That output then gets fed into this ALU out, which feeds into another register here. That register then goes out and gets buffered onto the bus, the shared bus. Once that, and then you can also output this onto just the output bus in general. And then we have a couple more inputs. We also have our A and our B input. We have our write enable to write to these registers or RAMs. And then we have our ALU select line, which has basically a demultiplexer inside this RAM, this ALU, which basically chooses which operation you're doing. And this matches up to the demultiplexer that controls this whole thing. So we have this part that feeds the instructions into the CPU, and then on a breadboard later, I have a demultiplexer on it that, tells this when to operate, and so when for these two to communicate. I did have this working about a month ago. I don't have a physical demonstration right now, as I've been solely working on my third and hopefully final version of it. So this is just a pretty basic sample. This is version 2. And then version 3, which I've been working on right now, is this. This is a FPGA. Now, at first, I had no clue how to get my CPU design actually on, a physical chip. Getting a design on a physical microchip costs millions of dollars, hundreds of thousands if you want it fabbed. And, I obviously don't have that kind of money. And I did not realize FPGAs existed until I stumbled across a YouTube video. And it got me quite excited because I could build anything I wanted into these programmable logic blocks. Now, I'm sure most of you are familiar with an FPGA, but if you're not, it's basically you can program these logic blocks in here as massive lookup tables or LUTs and chain them all together to form some sort of logic. Now, I programmed my CPU in Verilog, and I have the Verilog program actually on here, and I have it calculating the Fibonacci sequence. Actually, now, this is an 8-bit version, since, it's on an FPGA, and so I just have to change one parameter in my program to make it as many bits as I want. In theory, I can make it 128 bits, since this is a Tang Nano 20K, and this has 20,000 programmable LUTs. And so this allows for a lot of freedom. Sorry, I'm just plugging in my USB cable. A lot of freedom when designing things. So it should calculate the Fibonacci sequence. This is the first 4 bits. And so we should see, it does take a little bit. So while I'm talking, I'll let it run right here. So this is my clock module I made. It's simple, just creates a nice little square wave. You'll notice these two chips look oddly familiar to this right here. This chip looks really familiar to this thing right here. And it's literally a copy and paste. It's literally the exact same thing here. It just creates a perfect square wave for the FPGA. Now I know the Tang Nano 20K does have a clock generator and can create, I think, up to a 6 megahertz, maybe a 10 megahertz clock signal, which for later actual programs, I will run on this thing. And my Verilog program consists of about 500 lines of code. Most of that is basically just describing the instructions. My thing has 16 instructions, including the no operation, so really 15 usable instructions. And most of those instructions are actually just ALU instructions. So we have just add, subtract, and, or, not, XOR, not, all that stuff. And so you can see it's counting here. I think this is only outputting every 2. So I think I saw 1, 3, 8. And so it's really 1, 2, 3, 5, 8, and then 13. But as you can see here, I'm only outputting every 2. So it's, yeah, there we go. Okay, so this is the FPGA version. I'm gonna go over to the computer now. I'm gonna show you guys how the Verilog program actually works and have it running. See you guys there. Okay, so at the computer, we have our Verilog program for the FPGA. As you can see, it's 518 lines of code. Most of that is actually taken up by this instruction defining over here. I'm just in VS Code right now, analyzing my, Verilog program. We have our actual Verilog program right here at the top. We have our physical constraints file for the FPGA. We have our program, which goes into the FPGA and gets programmed into the memory. We have our 3 supporting Verilog files. So we have our ALU, our counter, and our memory. And our ALU, it's just very simple. We have our A write, B write, because inside the ALU we actually have our A, B, and C registers. So all of our registers are actually in the ALU. And then we have our select input here as well. The select input just checks, which operation do you want to perform. For example, if you want to do the first operation, that will be add. If you put in a 2, that'll be subtracting. And so this is one of the most viable base Verilog modules for my top module. Second, we have our counter. Our counter is even more simple. It literally just takes in a clock input, which is from that clock module I showed you guys earlier, and it outputs a just a 4-bit signal. It also includes an increment, a reset, a load signal, and load pins. So if you want to jump to a certain line, you just have to put load signal high, and you have to load pins with the line you want to jump to. I.e., if you want to jump to line 5, you put load signal high, and you put 5 into load pins. And this is just the logic for that to function. Next, we have our memory. This is our RAM. It's quite simple. It's just a register that is 2-dimensional. So we have our 255 lines, and then since it's this is actually 2 bits, but we'll change that later. But this will be 4 bits or something wide, and then 2 bits long. And then our top module, we actually instantiate all of these, as you can see here. So we use these. So this incredibly large program, it doesn't even get any larger. So we use these modules just to make the reading a lot easier on the user. Okay. Again, our inputs and outputs for the CPU is actually incredibly simple. We have our clock input, as you saw on the diagram before, and you have our out input. The data is actually stored in the memory itself. So in initialize here, you see that we have read memory binary program.bin. So we're actually reading this binary file that is created from a compiler that I made that I'll show you later. But it's reading this binary file and putting this into the flash memory of the Tang Nano and putting this as the variable program. That's why you don't see here in input, you don't see a program or data input here. That's why, because it's getting read right here. Our general purpose components, this is just housekeeping stuff. So you have our monitor, ROM address out, which basically before this I actually had EEPROMs to go with this. I don't know if you saw that in the previous video, but there were EEPROMs, and actually there was an input for data, but this basically just tells you what address or instruction you want to read from. So this will increment every time the increment count flag is pulled high, it'll increment its value. So it'll go 1, 2, 3, 4, 5, 6, etc. all the way to infinity, unless the halt option is pulled high. And then this whole CPU in Verilog is a massive state machine. So we have our state registers, so we have our high level state and our low level state. The high level state determines if it's on the fetch, decode, execute to, or clear cycle. And then we have our low level state, which basically just determines what, instruction we're actually on. So you can see here we're on the store instruction, and so it'll do this command here. We'll get into that later though. Okay, next we actually define our states right here. So we have our fetch, decode, said that earlier. I assigned them a binary value, basic state machine. And then our low level states, this is just defining all my instructions. You're willing to pause the video and take a look if you want. But we have 16 instructions, 15 not including the no operation, but pretty basic instructions. We're just loading into registers, storing to RAM, as you can see here. Jumping here, we have if jump, conditional and unconditional jump. We have our halt output, and then we have our arithmetic operations. And then this is how you actually load a number into the CPU. After that, we just have our control pins. So this just defines how to work with it. So as you see here, once we instantiate ALU, you notice that ALU execute goes with the execute line on the ALU. So actually open that up. So this ALU execute goes to this input right here. Just defining modules in Verilog. And as you can see here, I have the parameter 8 bits. So if you notice, most of my general purpose components, since as you can see here on my counter, I actually set the parameter to 4 bits. So if I want it to 8 bits, I would have to define the parameter, which, where is it? General purpose components. You see most, so it's like I could change this to 12 and have a 12-bit computer, and so each command would have 16 bits, 4 bits to the instruction, 12 bits to the data. 8 bits is just nice and clean, it's easy to understand. It doesn't take that much space up LED wise. So 8 bits is good. You could set this to like 2 bits if you wanted. I don't think that would be useful, but you could if you wanted. They over initialize. This is just loading zeros into anything, so we don't have anything floating or any weird behavior. So we're just loading everything 0, and we're also reading the program. That's important. And we're also enabling the CPU. That's very important. This is how the halt command works. It basically just sets CPU enable to 0, but we want to set that to 1 since we want it to work. Next, we have always at the positive edge of the clock. You could set this to negative edge, but I believe that would create an error because this is all my base modules are based off the positive edge. So you want everything to be linear, everything to be based off the same positive edge clock. So that's why I have this here. So every positive edge, it does something inside my state machine, moves states, does the task inside a state. And then you can see here, this is me loading the new instruction into the command from the program or ROM address out. Next, we have our first thing, which is our fetch. Our fetch basically just states that, current instruction and current data just loads in the value from instruction in and data in. So current instruction and current data are just general purpose variables that the rest of these use. So every time a new command is updated, this instruction in and data in will actually get updated, because in the general purpose components, we see that instruction in is the first 4 bits, and the data is the first 8 bits, and the instruction in is the last 4 bits. That's because if you notice in my program, these are 12 bits, even though it's an 8-bit system. So we have the first 4 bits. Where's a good example? First 4 bits is the instruction. So we have these 4 is the instruction, and then these 4 is the data. And then this is basically just splitting that up into 2. So we're splitting into 1 is the instruction and 1 is the data. That's why I have instruction in, data in, and then here we're just calling it, and we're making sure we set increment to 0, because if you set increment to 1, then the command would update and the program would go to the next line, and then it would mess with the state machine, as now we have different instruction and different data. Next, we go to the decode cycle. As you can see here, high level state goes to decode, so we're moving to the decode cycle. Next, we go to the decode cycle, which is basically just checking if the current instruction is equal to load A or load B. Again, that's with the low level states, as here, they're parameters, so they're just numbers, so they're just checking if the input, which is this first 4 bits, is equal to some command from the low level states. If it is equal to that, then it performs these operations here. I'm not going to go too in depth for each single one, since that would take a long time. But the most important ones are like the store, the load number, and then all the arithmetic ones are basically the same, as they just load a select line and they put ALU execute high and they perform that operation. Store works by enabling the C out, which basically enables the C register and the ALU to go to output. It enables write enable for RAM. So RAM is waiting for data to come in, and we see RAM address goes to current data. I must have put an extra apostrophe there, sorry. RAM address goes to current data. Current data is like your data input. As you can see here in the fetch, current data is equal to data in, and remember that data in is equal to the first 8 bits of the instruction, or last 8 bits, so these ones right here. As this one's all zeros, this one's, this one's 1, so yeah, just loading that. And then after that, it goes to all the instructions go to the execute phase. Only some instructions go to the execute to phase, as all the instructions that need to deal with RAM need an extra cycle to wait for the RAM to actually update. That's why I have another state right here. It uses another clock cycle, which is, not ideal, but it was necessary for some of my instructions to work, because when I was using Icarus Verilog to analyze the output of the CPU, there were varying responses. It was, very undetermined without the second clock cycle. And then all of them again have clear. This is basically just setting, all of them to 0, so we don't, leave stuff floating or anything like that, in case it breaks or something. And then, yeah, this is the Verilog program. I actually have GTK Wave right here, and this is what I use to simulate it. Where is it? Downloads, go test bench, VCD, and so, you know, this is how I tested everything. Incredibly useful, highly recommend Icarus Verilog. The built-in VS Code wave analyzer just sucks. Maybe I don't know how to use it. That could just be me, but I tried using that. Did not work very effectively, to be honest. Yeah, high level state, low level state, current instruction, current data. And then we have our, where is it? RAM, write enable, read enable, out, execute, data, address, ALU, you know, AREG, BREG, CREG, cout. And so, you know, this helps us analyze the actual, this is my test bench module, which is running on a program I wrote earlier. The one we have right here, this is actually calculating the Fibonacci sequence, and as you saw earlier, it only did every like 2 numbers. It did like 1, 3, and then it did like 8, and then 21 or something. So it skipped, you know, 2, 5, all those ones, and that's because I'm actually missing a line where it outputs, you know, a second time, which I'll show you in my compiler. And so I actually built a compiler because, you know, writing this binary by hand would be a pain in the butt, and, you know, trying to decode this even harder. So, you know, I wanted to have a physical, like, string version of it. So I built this Python compiler. It's super simple. I just use a dictionary to search up, you know, words in, you know, my text.txt file or my programmer.txt file, and then assigns that word to a value. And then this is basically just stripping these lines, so cutting them in half, making sure they're, you know, stripped in half so they don't have like the new line character, and then associating these lines with, you know, values, as you can see here. So this is like 0xf or 15 in hex, and then this gets appended to raw bytes, which gets written to text.bin right here. Actually, we can do that right now. As you can see here, we've out1 right after store into the first address of RAM. And the reason it wasn't working before is because we actually didn't have a out2 here. And basically this is storing, the stuff before it stores the output into address number 2 of RAM, but we're not actually outputting the second address of RAM. That's why we saw the skipping intervals until I actually save this and then run my program. We should see that the new updated program should have this line right here, which is true. So we have 0010, which is, where is it? I have it, sorry, the third line. So it should be this one. This is the new line we added, which should be, what, 0111, which should be the output. Where is it? 0x7, right? That is correct. And then we have 2, which is, you know, 00010, which again is 2, which is correct. And then this, this bin file gets this, this current Fibonacci sequence gets deleted, and then you just transfer the bin file over to this, rename it to program.bin. The only reason it's saying program.bin is because the actual, this top.v file, it just checks to see if there's a file named program.bin. You can change that if you want. Yeah, here it is here. If program, this, I could change it to text.bin. I just thought program.bin was fitting for the name. And then, you know, you have to make a change, save it, and then actually I am in the virtual environment, so I can say opio build, which is good, and then I can go over here and grab my FPGA that I grabbed just a second ago. Oh god. Okay, I grabbed it, plugging in the FPGA, and then fingers crossed it doesn't give me a USB bulk write error. That's been happening lately. I'm not really sure why. Probably should look into that, but it's not frequent enough to annoy me. So unless it happens now, that'd be bad. So I say opio upload. It waits. There we go. It's working. It writes it, and then hopefully now it should be calculating the Fibonacci sequence once it finishes writing and reboots. I have all this is open source. I have it all on GitHub. I have the compiler and the Verilog program in GitHub. I need to put my schematics for the PCBs on GitHub, and I also need to show you guys the picture of the PCB version, or the breadboard version. And I appreciate you guys for watching. Thank you. I'll come out with updates for this one. My next project will be a UAV, or unmanned air vehicle, I think, and I want to integrate my CPU into that, where it scans like terrain data using a topology sensor or something like that. Anyway, I appreciate you guys for watching. Thank you.